All right, thank you very much. Thanks for the opportunity to talk here. So I actually have a more or less impossible job now, right? Because the person who was going to be speaking this morning was Astrid Den Hoof from Victoria University of Wellington. And Astrid gives amazing talks, and I always love listening to Astrid's talks. So then being given the job of having to fill in for Astrid is a tough gig, right? So, and then, as Nadia alluded to, I prepared this talk sort of kind of at the last minute a little bit because we realized we didn't know until late that Astrid couldn't get here. So I kind of prepared the talk in Singapore airport and then on the plane. And then I got here this morning and opened my bag to just look at what I was going to say and realized that I left the talk on the plane. So now, let's see how this goes. But it is a real pleasure to be back here in Edinburgh, and it's a real pleasure to speak here. And I want to also particularly acknowledge before I start the enormous amount of work that Mark Lawson has done. I'm sure that we'll hear this plenty of times this week, but whilst there were a number of organisers of this conference, there was really one organiser of this conference. And thank you very much, Mark. All right, so Astrid's title, and I decided I would try to guess what Astrid might have wanted to say to you. The title, to Astrid's title was C-star algebras, no, groupoids. From the C-star algebraic point of view or something like that. Does that sound right? It's close enough. So what I thought I'd do is try and basically explain why I think it is that C-star algebraists are particularly interested in groupoids and why groupoids are such a good picture from the point of view of C-star algebras. So I'm going to start basically from the point of view that maybe we don't all know what a C-star algebra is, or maybe we do, but we've only seen the definition once or twice, or whatever. Maybe we should just start from the start. I'm going to go straight to those C-star algebras that are most closely aligned with groupoids and why the groupoid picture is so useful in dealing with them. That's my idea, right? So our starting point is just that a C-star algebra is an abstract. So a C-star algebra, abstractly, is just a star algebra with a norm, which is submultiplicative. And then it needs to be complete in that norm. So I should say that it's a complex star algebra. Complete. And it needs to satisfy the C-star identity, which is that the norm of any element that looks like this, the norm of A star A is always the same as the norm squared. All right, so that's my starting point. I'm thinking of C-star algebras abstractly as just Banach star algebras that satisfy this perhaps initially weird looking identity, but if you think for a second about where this might come from, it's not so weird. So the first example, of course, is just the complex numbers, which is a star algebra if you take your star operation to be complex conjugation. And then this looks very familiar because the first thing you see in first year maybe is that this is the same as this, right? Okay, so that's our first example, just the complex numbers under complex conjugation. And then the second example would be maybe Mn of C. So now A star is the conjugate transpose. And then what's this saying? So when I say that the norm of A star A is the norm of A squared, really that just boils down to the spectral theorem, right? I take a matrix that's nice enough, I can diagonalize it, and then the eigenvalues tell me the norm of the matrix. So that's what's going on there. Okay, and then there are two. So every time anybody starts talking about C-star algebras and says it's, abstractly it's this, and then I'll give you some examples. They always give the same 4 examples. So I'll give the other 2 examples that people always give, and then I'll explain why that is, right? So the next example would be, I take a locally compact Hausdorff space X. I take all the continuous complex valued functions on X with the property that for any given epsilon, the set of points on which the function value is larger than epsilon in modulus is compact. So they sort of vanish at infinity is the idea, right? So I can make this into a star algebra with pointwise operations. And the norm on it is going to be the supremum norm. And then it's really easy to convince yourself that it satisfies the C-star identity because pointwise is just what happens in the complex numbers, right? So there's not much going on on there. And then the last example that people always give is maybe I take my favorite Hilbert space H. I take all the bounded operators on that Hilbert space. Anytime I've got a bounded operator on a Hilbert space, it has an adjoint. Right, so the functional analysis that if you've got an operator on a Hilbert space, then a bounded operator in a Hilbert space, there's a unique adjoint for it that satisfies this identity, right? Now the C-star identity takes a little bit of proving, but it's not too bad. You sort of just do something like you would do with matrices, except with respect to a chosen basis. And there's lots of different ways to prove it. Yeah. And of course, if I've got a C-star algebra, I guess I can always take a star subalgebra of it that happens to be closed in norm, and that'll also be a C-star algebra just because the only thing that doesn't immediately pass to a subalgebra is the completeness. So as long as it's closed, I get another example. So or closed star subalgebras. All right. So why are these always the same 4 examples that people give every time they start talking about C-star algebras abstractly? Because of some theorems. So I'm going to give you 3 theorems. So one, so let's say A is a C-star algebra. So firstly, if A is finite dimensional, then A looks like a direct sum of matrix algebras. Finite direct sum of matrix algebras, right? I want to just say something about how you prove that. So how would you go about proving that? Well, obviously there's going to be lots of steps involved, but the fundamental idea is, so why? You just choose a massimal abelian subalgebra. It's finite dimensional and commutative. So it's going to look like, you've got to do a bit of work here, but it's going to look like a direct sum of copies of the complex numbers. It's finite dimensional. So this looks like a direct sum of copies of the complex numbers. And that gives you coordinates, right? So the idea is that gives you a set of diagonal points or something that are going to be the diagonal elements in your matrix algebras. And now you just look, okay, amongst these subalgebras of complex numbers, which ones can be gotten to from another one by multiplying by elements of the C-star algebra? That breaks it up into a bunch of equivalence classes. Those will be the summands. You got to do some analysis, but that's basically the idea of the proof, right? So where this comes from is you choose a maximal abelian subalgebra, that gives you some coordinates, and you work from there. Lots of different choices of maximal abelian subalgebras, but it won't matter which one you picked. All right. So finite dimensional C-star algebras look like direct sums of M, N, and C. That accounts for these 2 examples, right? That we always give. Okay. Second, if A is commutative, then A looks like C0 of X for an appropriate choice of X. So every commutative C-star algebra is one of these ones. Why? Well, I'm not even going to try and prove this, but I will say X is the characters of A. It's just homomorphisms from A to the complex numbers. Yeah. And I just want to point out that that means that we can often think of locally of C-star algebras as algebras of functions. Because if every commutative C-star algebra looks like this, then in particular, if A star A is A star, if we've got an element of a C-star algebra that commutes with its adjoint, then it generates a commutative subalgebra, and I can close that up and get a commutative C-star algebra. So it's a continuous functions on something, right? I'm going to sort of fudge whether there's a unit or not here, so please ignore the fact that I'm not being very precise. Then C-star of A looks like C0 of something, or maybe it's C of something if I throw the unit in, but I'll just say C0 of something for now. And what's the something? It's the spectrum of A. Right, the set of almost eigenvalues of A, right? Complex numbers lambda, so that A minus lambda times the identity. Oops, I just used an identity. Don't worry, it doesn't matter if is not invertible. Which means that I can sort of apply functions with a suitable domain to elements of A that look like this. So I get correspondence. It's actually an isomorphism. C0 of the spectrum of A. C-star algebra generated by A. And what we do is we write F goes to, we just write F of A for the corresponding element. I'm going to use this in a second, so I just want to point that out. But anyway, it's a really important technique. And it sort of means that locally C-star algebras look like algebras and functions. Okay, well, that accounts for this example. There's only one left, and this is this B of H thing. So it better be everything, right? Because otherwise I've left something off the list. And that's what the third bit of the theorem says. So 3, no hypotheses. A is always isomorphic to a closed star subalgebra of B of H for some choice of H. Okay, so why do I even need 1 and 2? Why don't I just use 3? Well, because for 1 and 2, it really told me some stuff and it was quite useful. But for 3, there's nothing particularly, I mean, it's canonical in the sense that there's a canonical way to construct H. But how do I get this? Well, it's hard work. A acts on itself by multiplication. I look at all the different ways that I could turn A into a Hilbert space by completing it with, well, actually quotienting, then completing with respect to some norm. That gives me a great big representation of A. And then I apply the Hahn-Banach theorem to show that there are enough such representations so that I wind up with a faithful representation. Great, but there's no canonical basis for this Hilbert space. There's nothing especially nice about the way that A acts on the Hilbert space with respect to any particular basis. I don't know a lot about which operators on that Hilbert space are in the image of the C-star algebra. So it can be a very useful theorem, but it's not like these first two where I've got a concrete description. This one, I'm really going straight to non-constructive stuff just to get the Hilbert space in the first place. Okay, so those are the 3 sort of big theorems that people always, and I should say, so these are the Gelfand-Naimark theorems. I'm not really sure exactly who to attribute this theorem to. I learned it from Takesaki's book, but that's not where it sort of came from originally. Okay. So those are the 3 big theorems that you always see, but there's another theorem about elements of a C-star algebra that I think is really helpful in understanding the relationship between C-star algebras and groupoids in particular. It maybe doesn't usually get stated in this context. I want to say what that is. So my point is here we say every element of a C-star algebra acts on a Hilbert space, but I don't know much about the Hilbert space. I don't know much about how it behaves. But here's another theorem that says something about how elements of C-star algebras can behave when they act on Hilbert spaces. And it's polar decomposition for an operator on a fixed Hilbert space. So here's another theorem. So if A belongs to a C-star algebra, I can put his C-star algebra on Hilbert space. It's got a faithful representation on Hilbert space, right? Well, let's just ignore that for a second. For any particular choice, for any choice of representation of A on Hilbert space, I can do the following polar decomposition. I can write A as V times, I'll write the square root of A star A, where V is a partial isometry. And this guy is a positive element. It equals B star B for some element B. So this guy here lives in a C-star algebra like this, the C-star algebra generated by a particular element. I've applied a function to an element of the C-star algebra. It's exactly an instance of this second theorem, and it's a positive function. Right? And it's going to be 0 precisely at 0. So in fact, it corresponds to the function on the spectrum of the element that is x goes to the, or z goes to the square root of z, which makes sense because the spectrum's positive, because it's a positive element, blah, blah, blah. And this V is a partial isometry. So what do I mean by that? I just mean that if I put it on Hilbert space, then V restricted to the kernel of V perp is an isometry. Right, so what does V do? It sort of cuts down to some closed subspace of the Hilbert space you're sitting on, and then it maps that subspace isometrically to somewhere else. So I could choose a basis for the domain, and it would be sent basis element by basis element to a basis for the range. So this is really, this is quite useful in the sense that, okay, I know something about the positive element here. What's more, I guess I already know now if I replace this positive element with anything else that has the same support, anything else in the C star algebra generated by this A star A, it can be represented with the same V sitting in front of it. And so really what I've got is sort of a continuous function at somewhere, and then it's being moved to somewhere else by this partial isometry V. Okay, so why is it that that theorem doesn't get mentioned so much when we talk about sort of C star algebras abstractly? Well, because it's only one element at a time. And if I look at all of the elements of a given C star algebra and take their polar decompositions like this, the V's are not going to play very nicely with each other. There's no compatibility between them at all, right? The subspaces that they move isometrically around are not necessarily orthogonal to each other or don't intersect each other nicely or anything like that. They're just all over the place. And so there's no really good way to patch all of these polar decompositions together into something nicely behaved. Okay, so we're mathematicians. If we've got a problem, we just try and define it away, right? So let's see if we can define away the problem that we can't patch these things together and see what we can say. So, going to define, this is really Renault, I guess. So a cartan here is a pair of C star algebras, A and D. V sits inside A as a maximal Abelian subalgebra. So think back to our matrix algebras example where I was trying to argue that every finite dimensional C star algebra is matrix algebra, right? So D is a massa. I'm going to put this down. I don't really need to write this, as David Pitts explained to us a couple of years ago, but I'm going to write it down anyway. So D contains an approximate identity, A. Right, so that is any element of A can be approximated by multiplied products of things in the C star algebra, but products of itself with things in D. And then, two extra conditions. There's a norm decreasing map phi from A to D. It has to square to give itself, so it's a idempotent, and has to preserve positive elements in the sense that if it hits a positive element, you get 0, then your positive element was 0. And then lastly, A has to be the span, closed span, of right n of A. N stands for normalizers, and the normalizers of A are elements n such that n of D. N star D n and n D n star are contained in D. So they conjugate this chosen the vacuum itself. I just pulled that definition out of nowhere, right? What's that got to do with what I was just saying about polar decomposition? Well, the point is that if I take the polar decomposition of one of these normalizers, so I've got one of these diagonal subalgebra like this, one of these cartan subalgebras, let's take the polar decomposition of one of these normalizers. So remember, D contains an approximate identity for the whole C star algebra. So if n star Dn is always in D, then in particular, if I put an approximate identity for the C star algebra here in the middle, I'll always be in D. These are closed star subalgebras, so when I take the limit, I'm still in D. So n star n itself belongs to D, and then n star belong to D as well, right? So if n is a normalizer, then n star n and n star are in this commutative C star algebra D. D is a continuous functions on some space, right? That was our second theorem about commutative C star algebras. They're all C0 of something. And in fact, the something is the characters of D. So we know what n star n and n star kind of look like, right? And now what does the polar decomposition do? So n is sum v times the square root of n star n. Well, if n star n is in D, then when I apply a function to it, I wind up back in D. So this root n star n was in the C star algebra generated by n star n. So in particular, it's in D. So this here is again in D. So it's a function on some set. So I'm going to say, I'm going to write, so this gives two open sets. And just to be clear, when I say support here, I'm actually taking the open support. So I'm not, as usual, usually you would write support means the closure of the places where it's non-zero, but I mean just the open support here, just the places where it's non-zero.
Then I missed, can you repeat the identity?
Oh, sorry. So it's a like a local unit. So an approximate identity means, I will say that, well, it's not necessarily a sequence, so maybe a net, E lambda in D. So A, E lambda. So it's a net in D that has the property that when I multiply it on either side by an element of A, it always converges in norm to that element A. You're welcome. Sorry.
And just quickly,
yeah,
do you need that this conditional or this conjunctive map restricts to the identity on D?
Well, that tells me that it restricts to the identity on D, right?
What if you had what if D was a algebra that's isomorphic to a strict subalgebra of itself, and then you map D to that subpart as well?
Well, I guess I should say that it has to be surjective. So maybe if I just do this. I'm insisting it's
There should be a D there.
Sorry, where's that?
Where the normalizer is.
N is in the normalizer.
Just to see that, just, yeah.
Thank you very much. Any other things I've got wrong? Okay. Right. So what's going on here? So now I'm just going to suppose, so, okay, so N, take N a normalizer. That means that N star and N star are contained in D, and I can write N as this polar decomposition. Now let's suppose that the support of M star is equal to the support of N star, and likewise the other way around. So I've got two normalizers that have the same support at either end.
So that's an N and M on the left.
Oh, I'm sorry. Support of M star is the support of N star, and the support of M star M is the support of N star N. Is that better?
Where's your M?
I'm sorry.
Well, where?
So M and N are both in the normalizers. So suppose I take two normalizers that support at either end of the same. Well, then, okay, there's a little bit of work to do, but the V that we get when we do the polar decomposition is going to be the same V for both of them. And V M V star, V N V star, or V star V, so V is a partial isometry, V star V is going to look like the identity on some sort of subset of the Hilbert space, and you can prove that means that it acts as an identity element on the right of the M here, left of the M. So this is the same thing as V M N V star. And if I put V stars around the outside of all that, well, now I've got a V star V that again looks like an identity element somewhere, and this VV star here looks like an identity element. So, sorry, that should be a star.
You lose an M.
No, now this is just with N.
Oh, sorry, I thought you meant
No M. So the V star V behaves as an identity element here. So I just get N back. So what's that saying? This is saying that conjugating by V is a homomorphism, like multiplicative map on these things. This is saying that it's invertible because I can just conjugate by V star and get back to where I started. So it's an isomorphism. So N maps to V and V star is an isomorphism from from the support of n star n to the support of n star, or the algebra of functions on this. Those are just subalgebras of this algebra D of all continuous functions on D hat. Well, now we go back to our theorem about commutative C-star algebras. Every commutative C-star algebra looks like the continuous functions on something, and it's given by characters. So if I were to take a character at one end of this, like I were to take a character of the C-star algebra of n star n and compose it with this homomorphism, I'll get a character of the C-star algebra at the other end and vice versa. And that's enough to tell you that this isomorphism must be induced by a homeomorphism between the spectra. So this is homeomorphism. Alpha n, I'm sorry, from the support n star n, support star. So what is that saying? That's saying that if I've got a Cartan pair like this, they're built from sort of local isomorphism or local homeomorphisms of a fixed coordinatizing space Z hat, space of characters of the subalgebra. Now, not every element of the C-star algebra is one of these local homeomorphisms, just the normalizers, but the normalizers span it. Right? So the C-star algebra is somehow built in a canonical way up from little local isomorphisms of this coordinatizing subalgebra. All right.
So just because I'm not quite following the whole thread, but for any element of the algebra, taken on Hilbert space,
yeah,
the isometry and the polar competition will give you this kind of.
That's right.
But there's some connection between different ones.
Yeah.
Happen when they have the same support.
That's right. So the point is that what's happening here is now, at least amongst the normalizers, I can patch together the subalgebras, the subalgebras generated by the n star n's or whatever. I patch them together into a single big commutative C-star algebra. So they're all commuting with each other. And somehow what's happening is that I don't just locally have a little space and then a homeomorphism of that space. What I've got is a big space and homeomorphisms between little subspaces of that big space.
If you have two normalizers that don't perfectly match up, like you said, their intersection, and
yeah, you take their intersection and it would patch together to give you a little homeomorphism on their intersections. That's right. Now, maybe their union doesn't give you a normalizer, but at least you can patch them together locally on intersections. That's right. All right, let's just try and so I go to quarter fast. Is that right, Nadia? Have I got an hour or have I got 50 minutes or what have I got? Yeah, I mean, yeah, quarter past including questions. Good. All right, so let's just look at an example, like a really simple example, just to see what's going on. Because this was all very abstract and stuff, right? So what's the simplest example that we could think about? Well, let's go back to our MN of C example. So it's just the n by n matrices. What's our favorite maximal abelian subalgebra of A, or the diagonal matrices? All right. What are some elements of the matrix algebra MN of C that are going to normalize this diagonal? So I want elements so that I take a diagonal matrix, I conjugate it, and I get back another diagonal matrix. Well, there's a pretty natural set of elements that does that, and that's the matrix units. Right? If I take the matrix unit theta ij, it just takes scalar multiples of conjugation by it, just takes scalar multiples of the jth diagonal entry to scalar multiples of the ith diagonal entry. Right? So some normalizers at least. Theta ij. And every normalizer is going to be a sum of things like that, right, where each j appears at most once in a second coordinate, each I appears at most once in a first coordinate. So they can be sort of parts of a unitary, possibly multiplied by some numbers. Basically look like that. All right, so then when I do the polar decomposition, there's not really much to do here. It's easy to do a polar decomposition of a theta ij, right? Theta ij is just theta ij times theta jj. Perfectly good polar decomposition, yeah. So what's the spectrum of this commutative C-star algebra here? What is this the functions on? Well, I mean, it's just diagonal matrices, right? It's just tuples of n numbers. So it's just functions on the set 1 up to n. I'll pretend that they're actually continuous. It doesn't matter because it's discrete, right? So it's just got an endpoint spectrum. This normalizer here when I do the polar decomposition. So what's the support of this thing? Well, it's just one of the points, right? It's just the support is just n. So the support, sorry, it's just j. And then what does theta ij do? What's the homeomorphism of this 1 point set to whatever other 1 point set? Well, it's not very hard to be a homeomorphism of 1 point set. So it's just the map that sends the element j to the element I, right? So alpha theta ij is actually the map j goes to I on the set j, from the set j to the set I, whatever, right? Okay, so it's all very concrete here, and it just says the matrix units sort of locally just act like little maps between bits of the diagonal, and that's how the C-star algebra is built. It's built up from those things, right? So the point is, when I say, this is why I say it's like this D is like a coordinatizing subalgebra, it sort of tells us that the C-star algebra has elements that make it look a bit like this, except maybe the spectrum is a bit more complicated than an endpoint set. So some topological space. But this is the picture that we've always got in mind when we think about these. All right. Now, halfway through the boards, just a bit over halfway through the board. I haven't mentioned groupoids yet. So I can get started on groupoids. So what's all this got to do with groupoids? Because so far all I've done is tell you about C-star algebras, and maybe you don't care about C-star algebras, so maybe you haven't had much fun so far. So let's see what's this got to do with groupoids. Try and link this up with groupoids, because that was the idea of this board. Okay.
Aidan,
Yes.
but you've written local homeomorphism there. You don't literally mean local.
I don't literally mean local homeomorphism. I mean a locally defined homeomorphism. So I actually mean a homeomorphism of a little sub. So it's like a partial homeomorphism as a whole space. Would be a better way to say it. And
It's between ovens, is it?
so maybe I should just write partial homeomorphisms. Because I am going to say the words local homeomorphism in a second.
To mean an actual local homeomorphism. To mean an actual local.
Yeah, that's right. I'm actually going to mean local homeomorphism. Just because I'm crazy that way. Okay. So let's try and say something about groupoids. So I guess if I had to stop now, I would finish the talk by saying the whole point of groupoids from the C-star algebraic perspective is that they give us an algebraic model for this. That's some way to encode all of this algebraically, topologically, without having the C-star algebra there. We can get the C-star algebra back. Let me explain why I think that is. Okay, so I guess I didn't say this at the beginning, and I really should have. So none of what I'm talking about is any work of mine, right? I'm talking about other people's stuff, and I'm not saying whose stuff it is. I will say some names, but there's lots of times probably where I already have failed to give credit to you. But I'm definitely not talking about anything that I've done. I'm talking about other people's work. All right, so what's a groupoid? So I'll put the word groupoid here, and then I'll put in parentheses because I'm never going to say it, but I'm always going to mean it. So Tal Hausdorff. So I'm sorry to those, and you're absolutely right, who would have me talk about non-Hausdorff groupoids here. They are important, and there's lots of good reasons for studying them, but just to keep this as manageable as possible, I'll just talk about Hausdorff groupoids. And there's also lots and lots of reasons to think about groupoids that are not a tail, but I'm also not going to do that because then I wouldn't be able to justify my sales pitch. So I'm going to stick to the ones that.
Isn't Astrid more of a fan of non?
Yeah, well, so this is where maybe Astrid would maybe Astrid wouldn't have done this. Okay, so What's an Natal-Hausdorff groupoid? It's a locally compact Hausdorff space. I will give an example in a second, or some examples in a second. Curly G. It's got a partially defined associative multiplication. Continuous associative multiplication. So it's partially defined, so it goes from some specified subset G upper 2 of G cross G back to G. So there's this collection of composable pairs where I'm allowed to multiply them. Those ones get multiplied and wind up in G. And associative means what you think it means. So if GH and HK are both defined, then so is GHK, and it doesn't matter which way I put the brackets in. Yeah, that sort of thing. Right. That admits units. So that is given any groupoid element gamma, there's something that I can put on the left, I'll call that range of gamma. And something I can put on the right, I'll call that source of gamma. So that range of gamma times gamma is the same as gamma times the source of gamma. And inverses. It's not a formal definition, and it's not really the right way to write down the formal definition, but it gives you the right idea. So you could say a groupoid is a small category that admits inverses. You would sort of capture it. You could write down a careful set of axioms like you would for a group, except there's lots of them and they're kind of complicated looking. That specifies what a groupoid is. But think of it this way: it's got a partially defined multiplication, but everything admits inverses that work on either side, and there are sort of units to this thing. So, and I'm going to write G naught for all of the units. So these are all the R of gammas, and those gamma ranges over the groupoid. All right. Now that's just so far that's just a Hausdorff groupoid. All right. So what's going to make it a Tal? The range and the source maps really are in this time I'm there for real, are local homeomorphisms. Right, so they're defined everywhere, but around every point, there's a neighborhood on which they restrict to a homeomorphism. Okay. All right, so I should try and tell you what that's got to do with this picture over here, right? So suppose I take a point gamma in one of these things. Well, the range map is a homeomorphism on some neighborhood of gamma. The source map's a homeomorphism on some neighborhood of gamma onto open subsets of G naught. So there are U1 and U2, say, containing gamma, such that range restricted to U1, source restricted to U2 are homeomorphisms onto open subsets of the unit space. That's just because it's a local homeomorphism. I'll just intersect them. Then you've got a single neighborhood of gamma on which both the range and the source are homeomorphisms. Well, if they're both homeomorphisms, then I can compose one of them with the inverse of the other one, right? And then I get a single homeomorphism from some subset of G naught to another subset of G naught, right? So we get something which I'll suggestively call alpha U, that goes from source of U to range of U, and it just sends source of gamma to range of gamma. But that's a homeomorphism. Yeah. So what does that say? It says the groupoid is built from little partial homeomorphisms of some fixed problematizing subspace, namely this unit space G naught, right? Maybe there are lots of sort of open subsets of the groupoid that don't define such homeomorphisms, but it's sort of built from them. It's constructed from them in much the way that the C-star algebra here was constructed from these little partially defined homeomorphisms for the coordinatizing subalgebra. All right, so what are some examples? I'll just give you a couple of examples just so you've maybe got a mental picture of what's going on. So I think the simplest example that tells you something interesting is something like this. So I'm going to let G just be the Cartesian product of the set 1 up to n with itself, which I'm just going to think of the equivalence, the complete equivalence relation on the numbers 1 up to n, right? Well, it's not supposed to be just a set. It's supposed to be something with a partially defined continuous associative multiplication, blah, blah, blah. So I better say what those are. Topology is easy enough. This is a finite set, so it's discrete. I'm just going to take the discrete topology on it. But I better tell you what can be multiplied and then what the inverses and stuff are, right? So if I took an ij, well, so firstly, G2, there's things that look like this. So it's all the pairs of things in this relation where the second coordinate here is the same as the first coordinate here. All right, and now how do I multiply? Yes. Not many formulas that I can write down here that could possibly look right. I'll just ignore the J in the middle. The inverse is going to be JI. Just check that myself algebraically. And I'm going to identify G naught, which is really the set of pairs II with just the set 1 up to n. So I'm just not going to write I twice if I've got a unit and just think of I as a unit of this groupoid, right? What are the little, so I'm going to call these things, these sets U like this, I'm going to call them bisections. There's sections for both the range and the source map. They're only locally defined, but I'll call them bisections anyway. Possibly I should say local bisection, partial bisection, whatever. So what are the bisections here? Well, there's an obvious collection of bisections that I can write down, right? Because I can just single out individual points. So some bisections. So there's a family of bisections whose union is the whole groupoid, right? What's the local? We've done this before. I don't need to write it down again, right? What's the local homeomorphism that corresponds to one of these bisections? Well, it's just the map that sends, that's defined on the set containing J, that sends it to the set containing I, and there's only one thing it can do, right? Right. So there's an example. I'll give a second example. It's really a class of examples. So suppose that I've got, let's take a group gamma acting on a locally compact Hausdorff space X by homeomorphisms. Gamma's discrete here. Simplify things. Write down all the triples X, G, Y with the property that when G acts on Y, it takes me to X. One of the composable pairs, looks like what happened up here, right? So G2 all the tuples where the Y's in the middle match up. How do I multiply them? Ignore the Y's. And now I'm going to do something with the group elements. Well, what do you do with two group elements? Well, group operation, right? What inverses? YG inverse X. What's the topology? Just the, it's not quite the product topology, but it's inherited from the product topology. So this isn't the whole Cartesian product. But if I threw away the X's, I'd have the same information, and then it would be the Cartesian product and it would be the product topology. So there's actually no additional information. Sorry, I should say there's no additional information in writing down this X here. It's just that I don't know, somehow it's more symmetric. Maybe it's my sense of aesthetics. And also it just makes it really easy to see when things need to be composed and I don't have to mentally keep track of what the range of something is. So maybe I'm just lazy. All right. So that's the sort of thing we're thinking about when we think of one of these groupoids. It's kind of like a group acting on a space, but we're putting it all together into one. And they don't all have to look like this. It's just a guiding example. All right.
It's about the previous examples. Don't you get all partial bijections as bisections?
Yes, you do. Yes. So this is just a family of bisections. And again, if I want to get an arbitrary, I mean, what's a general bisection look like? Well, it'll be a union of things like this, so a collection of things like this, where each j can only appear at most once in the second coordinate, each I can only appear at most once in the first coordinate. So it looks exactly like the collection of normalizers that we wound up with when we did the example of the matrix algebras. So it's really exact matchup between, yeah, that's right. Yeah. Thank you. I should have said that. Okay.
And then here, do you assume anything about X in the second?
It's locally compact in Hausdorff.
Okay, so that's already.
Yeah. This is the problem with talking to C-star algebraists. Every X is always locally compact in Hausdorff. Okay, so probably got about somewhere between 5 and 10 minutes, and then we might have some questions. So I'll try and do it in 5. I just want to say how you match these two things up now, right? So I've sort of talked about C-star algebras in general. We wind up with this sort of local description. I've talked about groupoids. They are locally the same sort of thing as this. How do I get from a groupoid to a C-star algebra? That's not too hard. So given G, CC of G is a star algebra. So this is just complex valued functions on G, compactly supported complex valued functions. With a star algebra with, so the multiplication two functions is a convolution product. So it's just the sum over all the ways that I can write gamma as a product. And the adjoint looks like a complex conjugate, complex transpose, conjugate transpose. So gamma inverse. So think Laurent polynomials over the integers, right? The integers are a perfectly good groupoid. They've only got one unit. What's a function that's compactly supported on the integers look like? It's just a finitely supported function. So think of it as a polynomial. Right? So the value at n is the coefficient of t to the n. And then how do you multiply polynomials? Well, you just take, if you want to know the coefficient of t to the n, you look at all the ways to write n as p plus q, and you add up the coefficients. Yeah, so this is just what you would do if you're working with Laurent polynomials, or in a group ring or whatever you like. Yeah. All right, that's just a star algebra, but I can make it into a C-star algebra. So for each x in the unit space, I can build a representation. On the bounded operators, so on the Hilbert space, little L2 of Gx. So this just means elements of the groupoid that I can multiply on the right by x. So all the things in the groupoid whose source is x. Right? Because my groupoid's a tail, that's a discrete set. Because the source maps are local homeomorphism, that's going to be a discrete set. If G is second countable, it's going to be a countable set, but actually doesn't matter too much one way or the other. How do I define this representation? Well, I just think of it like I'm multiplying by doing convolution product, but with some point mass functions involved. So pi x of A acting on the basis element E gamma would be the sum source of alpha equals range of gamma, A of A, the alpha gamma. All right. If the source of gamma is x, then the source of each of these alpha gammas is going to be x. So I go from the right space back to itself. So everything works out okay. And that gives me a star representation, as it turns out. Well, if I've got a bunch of star representations of a C-star algebra on Hilbert spaces, in each of those bounded operators on Hilbert spaces, for each of those representations, there is a norm, the operator norm in B of H. So I can define a norm on CC of G. You've got to prove that it's a norm, but it is. So the norm The norm of A is just the supreme over all of these representations of the norm that it achieves under the representation. All right. And then C star R of G is the completion. So I can build a C star algebra from a groupoid. You actually do a little bit more. So if I were to take a complex line bundle over the groupoid, so sort of a bunch of copies of the complex numbers, one for each element of the groupoid, that was sort of a principal circle bundle, I could build another C star algebra that's twisted by that. I really just don't want to get into it, but you can do that as well. All right. And so what's the point of all this? Well, the point of all this is really two theorems. Actually, I'll state it as one theorem with two parts, but it's really. I mentioned Feldman and Renault. I'd really like to say Feldman and Moore here as well. They proved the corresponding theorems for von Neumann algebras before the C star algebraic theorems were proved, but yes, I'm talking about C star algebras today, so I'll mention Feldman and Moore, but I won't write it down. So the theorem is one, if G is an Étale groupoid, so Étale Hausdorff groupoid, then C star R of G, C0 of G0 is Cartan. So because the range and source map are local homeomorphisms, G0 is open and closed in G. So the algebra is just supported on G0. The functions supported just on G0 are functions on G. I should say topologically principal. Oh, so I'll say effective.
What does that mean?
I'm about to tell you. Thank you. So effective says that the set of gamma such that the range of gamma equals the source of gamma. That's a collection of things in the groupoid, right? I take its topological interior. Only the unit space. So what it's saying, if I look at the bisections, these local bisections in the groupoid, the only ones of them where the homeomorphism associated to it is the identity map on a little subset of the unit space are collections of units. That's all there is. You can sort of, I mean, it's actually not true, but you can sort of semi-imagine that if you had a groupoid that didn't look like that, you'd quotient out by something and get something like that. That doesn't actually quite work, but. Okay. And I should just say, saying goes. I didn't say what a twist was, but if you did twist the multiplication, you would still get a Cartan pair. And then two, this is a little bit, if AD is a Cartan pair, then what I'm going to do is I'm going to take the germs. How do I want to say this? So I can define the germ equivalence relation. This is going to be on normalizers and states. Sorry, normalizers and points in the space the hat that are in the support of N star N. It's the germ equivalence relation. So N by, sorry, let's put psi N phi. Let's say that alpha N of phi should be equal to psi, so I can make it as much as possible like the action groupoid. So psi N phi is equivalent to psi prime N phi prime. If phi equals psi, R equals phi prime, and alpha M agrees with alpha N on a neighborhood, which in particular implies that psi and psi prime are the same. And then the set of equivalence classes of these germs is a groupoid. And again, we can do this we can also recover a twist. Again, I haven't said what that is, so we'll just ignore it, but I can recover a groupoid from a Cartan pair. I can actually also recover a twist from a Cartan pair and these constructions. I'm mutually inverse. All right. So I said about halfway through that if I were going to finish the talk with one sentence, it would be, well, groupoids give us an algebraic model for what's going on. So now if I need to finish the talk in one sentence, which I do, I'm going to do that by saying this theorem describes exactly the sense in which groupoids are an algebraic model or local descriptions of C-star algebras as constructed from partially defined homeomorphisms of some fixed coordinatizing space, right? Given a groupoid, I can construct a C-star algebra, and it's not hard to see that the normalizers in this C-star algebra are exactly functions that are supported on local bisections. Those are the normalizers. So the local dynamics of the groupoid is the local dynamics in the C-star algebra with respect to this particular coordinatization. And conversely, if I've got a C-star algebra with a Cartan that gives us one of these coordinatizations, then it is the C-star algebra of a groupoid. It is described by exactly this algebraic structure. So it's almost like it's a non-commutative version of the commutative Gelfand-Naimark theorem. You need some extra coordinatizing data, but it's very much like that. And I think, for me at least, that's why, as a C-star algebraist, I'm so interested in groupoids, because this is the way I like to think about C-star algebras, and it gives me exactly the tool to make it precise.